On and regarding on. Okay, so today's lecture is lecture ID 11. So after today's lecture, there is just one more lecture to go, and that will be on next Tuesday. And that brings me a matter that we need to discuss, because according to the original plan, the next midterm exam is designed to be sometimes a little later in December. And my question to you, and this goes to online participants as well, is that what do you say if we're gonna reschedule exam week a bit, such that the exam would be in a week 49, and that week is the week where the Monday is December 2nd. How that sounds? Is that a problematic week? Because in that week there is a Friday that is official holiday, that's Independence Day. Is that a problem, or should we move that to week that is 50? That's a Monday 9th of December. Which one you prefer? 9 is better. Okay. Which is better? 5th. 50. Week 50. Okay, so that's the second week of December. Second week of December. Okay, so that again, week where the Monday is 9th of December. That's the best. I mean, that fits you the best, right? Well, yeah, of course, we can have it whatever time you want. So it's not a problem to me, but I'm just thinking that what is most, what is that you prefer? What is that is easier for you? For me, it makes no difference. So I'm not planning to participate in that exam, because for sure I'm not going to pass it. It's going to be so difficult. But this is for you. So second week. So it's again second week that you are preferring. So what about the online participants? I'm unable to see comments, if any comments. I'm checking my YouTube channel, but honestly, I'm even unable to find the streaming. Okay, sure. So I will set up the doodle questionnaire, asking what is your preference. And I will put the 3 options. First week of December, second week of December, and third week of December. And it's again 1 week. 1 week time that you will have to answer, to make your 2 attempts. Not necessarily need to make your 2 attempts, but at least 1 is needed. And then keep in mind, this is important. Keep in mind that if you select these midterm exams, then you don't need to participate in the written exam. There is one that is coming, I think, 16th of December. So if you did the first midterm exam and you're planning to do that, the second midterm exam, you can skip the written exam. And that's, what we discussed in the very beginning. That's, of course, is my recommendation too, because written exam, first of all, is awfully difficult. So it's like, it's vicious. So it's really, really difficult. So don't take that option. And whereas these midterm exams are automated, so it's my life too is more enjoyable when you select that option. Okay, but anyways, we'll set the dual little questionnaire so you can go and enter your answer regarding when the exam should be. Yes, sir.
Can you please update Socratic points?
Sure, I was thinking that they are updated, but they are not.
I'm not sure.
Okay, can you please check? Because what I do, how it goes is that after every single lecture, I get the results to my email. And then I forward that to one person in my team that is updating those semi-automatically. I mean, I don't do anything, but that person is taking care of that. But I was under impression that they always are updated, but they are not.
I don't think so.
Okay, so I could check that out, and also I would let you know how your points look like. Because remember, you don't need to score 100% from this soccer team, but I think that was like 60% is enough to get that upgrade.
So,
And
Well,
if-
yes, sir.
if we do good on Socrative exams, and then yes, and what about this? And we fail on this simulation thing.
Simulation assignment.
Yeah.
Okay, that's serious then, because simulation, there are two mandatory things that you must do. So you have to do written exam, and there are two ways to make it happen. So guys in the back, so please take a break with the computer business and listen to me. So okay, the question was again like how to pass the course, and this is important you too to know. So you have to do written exam. And two ways to make that happen. You can either do the midterm exam or written exam. And then another thing that is mandatory is a simulation assignment. I think that it is highly recommended to do it on time. Do it on time, even though that it may not be perfect. Still, timing what matters quite a bit. Because if you submit it late, you will automatically get some penalties. And the first thing is to make it on time, and they make something. The guys are flexible, so try to make your best effort to stay within the schedule. But those two things are required. Then the soccer team and these weekly homeworks are just something that helps you to upgrade your number, but that's it. They are not mandatory to do that. Clear? But you have another comment or question?
Yeah, because we skipped some of in-class quizzes in the slides.
Yes.
So the threshold is now lower, not the 15 points.
Sure, of course, I'm gonna upgrade that too. So I think at the end we skipped few, but now we still have this week left. And I will, of course, I will take a look at that's the way that the percentage will stay as it was originally planned to be. Yeah, sorry by the way for online participants that I'm moving away from the mic, and I'm unable to do that. I shouldn't do it, but yeah, we're gonna take care of that. Anything else? Because we're approaching the end. Last week will be the last lecture. And let me tell you something. Because I was kind of hoping that we can make a celebration in the last lecture. We can all be happy that finally it's done, so it's over, so we can move on in our life. This kind of celebration. And I'm thinking, if today we're scoring 100%, yes, but I think it's going to happen today. If we're going to score 100%, I will bring you some candies. Nice. Okay, so let's see. Because remember what happened last week? We scored like amazingly high. I think that it was a 96, 90, 99, something like ridiculously high. So I would like to redo that particular question. And I think today what will happen is that we're going to get 100%. So we'll see. Okay, and my camera is ready for selfie and everything, so we'll see. Okay, so what exactly we're going to do today then? Well, we're going to get started from the matters that are related to hydraulics. So I'm first going to wrap it up the hydraulic modeling business by explaining you how is that you can make the model of cylinder and a pump. So those are the two extremes. So the pump is where the energy is produced to the system, and then another extreme is a cylinder where the energy or the forces are delivered to mechanical structure. So those are the two things we need to study in order to complete the topic of hydraulics. And then we're gonna move on. I'm gonna shortly explain you a little bit about flexible bodies. Now this is a quite interesting topic, but is very wide subject matter, and it requires several lectures to have a good understanding about flexible bodies. I will give you an overview, and then in that course, which by the way is the best course in this university, if I have not mentioned that yet, the laboratory course, it's outstanding. It's just so much fun, you don't believe it. And then that is a course where I'm gonna close the explanation about the flexible bodies and many others too. All right, then next week, which is last week, we're going to look at the real-time simulation and gamification concepts. Okay, so with that, let's summarize what we discussed last week. And last week we first looked at the flow types. We concluded that in modeling perspective, we have two different flow types. We can either have a laminar flow, and in a modeling perspective, it's very important to understand that in that case, flow and the pressure difference is linearly related. So here's an example about the laminar flow, and look, how the flow and the pressure difference are related. So that's a linear relation. And that linear relation is something that depends on viscosity. So only in a laminar flow the viscosity comes into play, whereas in the case of turbulent flow, we can simply ignore it. Now, in case of turbulent flow, it's again important to understand how is the relation of these critical components that are flow rate and the pressure difference. And in this case, they are quadratically related. As the pressure difference is under the square root, so that's how it goes. So that's pretty much everything you need to know about the flow types. And then last week we looked how the different components can be modeled. And first we discussed that there are, in principle, three different approaches to model the components. First approach is fully based on analytical equations. And that would be all right thing to do, except that requires quite much parameters that may be difficult to get. Then another extreme is experimental models where everything is based on measurements. That's doable too, but requires a lot of experimental actions. So what we wanted to do is that we wanted to meet in the middle where we're combining these two features together. And we're gonna do that by using the method that is called semi-empirical modeling approach. The concept in short is such that we will get started from analytical equation, and here's an example how the model of a throttle valve look like, and that again includes some parameters that may be a little hard to get. Example is this diameter. That is simple thing to understand, but more difficult to get in a real life, and the discharge coefficient, which is this one here. Now we're gonna go and replace this original analytical equation by a semi-empirical equation. And in a semi-empirical equation, all these unknown parameters goes to semi-empirical parameter. And that's something that we can get directly from manufacturer's catalog. So that's the concept in short. So again, we get started from analytical equation. We're gonna do a little bit of mathematical manipulation such that parameters that are needed can be obtained from measurements that are provided in manufacturer's catalog. Clear? Makes sense? Good. Okay, and then we apply that to direction valve. And in the direction valve, which is a typical example about the component modeling, this model consists of two parts. First, we're gonna express where is the spool position. And that spool position, and now listen to me. So we're gonna first look at the spool position, which is expressed by using this equation. So physical interpretation of this equation is spool position, right? How it goes then? It goes such that, I have here input signal that goes into this magnetically operated valve. And then I have here like spool real position, and here's a time constant. So with this simple delay equation, I can express where the spool is located in any given time. And it's a function of control signal, right? So that's how it goes. Then once I know the spool position, then my flow rate is a function of spool position, and it have three different scenarios. Now, if spool is having positive position, then it's gonna connect the pressure port and A port as it is shown in this equation. Look again, I have here apps under the square root. because I don't want to play with imaginary numbers. So I'm just making sure that whatever goes in, under the square root will have a positive value. And then I have here my sine function, and the sine function will take care of the direction of the flow. And then I have here spool position, which is this one here, solved from that equation, or other way around, so it goes like this way. And then I have here semi-empirical parameter that tells me what's the size of this particular valve. Clear? Once again, physical interpretation of this equation is spool position, spool position, spool position. Oh, now it's a broken record. Okay, so let's move on. So that's the first scenario. Then the second scenario is that the spool is in a middle position. Then we are assuming that there is no flow whatsoever. And then the spool also may travel in negative direction, like this direction, and then it's going to connect A port to tank. And again, equation itself reminds, with no changes, it's just going to be the different ports that are connected. Clear? Okay. Are we going to have a candies next week? Let's see. This is going to be moment of truth. This is going to be, now if it's going to happen, if not going to happen now, then it's not going to happen in this course. That's how it's going to be. Because the next in-class quiz will be so difficult that you have absolutely no way to answer that correctly. Okay, so physical interpretation of equation below, and let me go back to this one. That the options are pressure drop to the valve, color of the valve, spool position, number of boards in the valve. So these are the 4 options. Only one is correct. Okay, so would you like to have some time to think, or is this done deal? Done deal. Good. But don't get this up-nose attitude. If you are a little bit shy about this, go ahead and ask and communicate with your fellow student, because we need to play safe here. Otherwise, the celebration is not going to be that fun celebration next week. Okay, so here's a little bit of side topic. I said last week that typically these direction valves are operated by magnet, and it goes such the way that operator is using a joystick, and joystick sends a signal to direction valve, and that's how the spool is moving back and forth. Now that's how it goes. And I just wanted to show you how that actually makes a big difference in terms of design. And here's I actually have here 2 different forest structures. The one that is having, which is I think it is like 50 years old, and then another one that is modern. And when you look at the design outside, yes, there are some changes, but the basic concept is still more or less with no significant changes. How come? I still have a diesel engine here, and I still have a hydraulics that is operating the crane, and I have tires here. Of course, this one is looking more modern, but the difference is not that significant. But there's a great difference when you get into cabin and you look how things looking in a cabin. This is how it look. This how things used to be, and this is how they are at the moment. What's the difference here? Here, if you look, I have here these sticks. These sticks are mechanically connected to spool. That's how you operate the system. So you have almost like a musician. So you have a lot of keyboards, and then you're moving them back and forth, up and down, and that's how the crane is going, moving and loading your tractor. Here, you have just the joysticks, and with help of these joysticks, you're operating your system. It's a great difference. And of course, there's quite a bit of software that helps you to do some of the tasks semi-automatically, sometimes even automatically. All right, so that's related to explanation about spool positions, of why they are joystick operated, why they are magnetically operated, just to make this cabin to look, something that is more productive. Okay, Now, ready to see how is the results from the in-class quizzes? Let me take a look. Okay. So is it going to be? Yes. So candies or not? So that's sad because I already purchased those candies. I'm gonna eat all them by myself. So you're not gonna get any candies.
I think somebody made it intentionally.
Intentionally. I think so too. You know, there's a sabotage. Close, very close. You know, this is exactly what happened on last Tuesday too. Okay. Okay. So, well, we still have the final attempt. You know, the one more in-class quiz, and then we're done. Okay. You know, let me just wrap it up. This and digital hydraulic was another thing we discussed shortly last week. And again, the idea is to replace the spool that is sliding back and forth with number of on-off poppet valves. And this, you know, is equal if you keep on adding the number of the poppet valves. And like we learned last Tuesday, the reason to do this is that you can have a hydraulics with a better efficiency. So efficiency can be enhanced with this approach. And this is still quite a bit under the studies, and there are people that are keep on developing this. But it seems that this is finally something that helps to produce or helps to make the hydraulics to be more efficient. Because again, the conventional hydraulics is all about the pressure losses, energy losses. So the control is based on not so clever concept because we keep on losing energy. And of course, what we would like to do is that we would like to produce, you know, right amount of energy in the system and use it all. And digital hydraulics helps us a bit in that direction. And then what I'm gonna do is that I'm gonna simply skip this next topic, which is pressure relief valve. I'm gonna just explain the concept, and I'm gonna read this to you, reading assignment to you. This is, by the way, quite painful reading. It's not a pleasant reading. But again, only those of you that are expecting to get 5 out of 5 from this course, I recommend to read. Rest, you can skip. Okay, so the pressure relief valve, this is how it looks. And again, you know, to make a model of this kind of component, everything gets started from analytical equation. This time the mathematics needed to convert these analytical equations to be semi-empirical equation will be involving, will be a bit painful. But anyway, so how it goes analytically goes like this. So flow rate through the pressure relief valve, which is, you know, the flow here can be computed analytically by using this equation where I have here discharge coefficient, then I have here spool position that is measured here, so X is here, and then I have here pressure. This time is not the pressure difference because it is assumed the pressure or this component is actually connected to tank. So the pressure difference is more or less equal than the pressure one, which is the one that is applying here. Because, you know, this in reality will be like this, but the tank pressure here can be assumed to be insignificant. So that's how the pressure difference is computed. Now the X, which tells you how is the spool position, that you can get using this analytical equation. And this is when things becoming really painful. Because here, you know, the parameters needed are mass of the spool, which already is in practical life somewhat difficult to obtain. And then the spring coefficient, well, that you can get, but again, is a little difficult to get. And then there is a pressure force, and then there is a flow force, spring force. I think that this should be spring force. There's this preloaded spring force, how much you're tightening the spring. These are all the force component needed. And in theory, it's possible to use this equation of motion and from this equation of motion solve the spool position and put it back here. But that will be in practical life somewhat painful. So that's why again these equations are converted to be in semi-empirical form. And in semi-empirical form, how it goes then is all these spool positions and diameters related to that will be replaced by one single parameter that is called semi-empirical parameter, and that you can get by solving this first order differential equation. Is physically not as accurate than the original analytical model, but way more pleasant to use in practical cases. Still, some of the parameters needed here, like C1 and C2, well, you need to get those, but those are the ones you can get from manufacturer's catalog, depending on the features of the valve. You can get those numbers. This is something that you can actually use a value that is assumed to be between these numerical sets. And once you have it all, then you can compute how much flow is going through your pressure relief valve. With this short explanation, I'm going to move on, and or is there any comments or questions? It's just a little painful component. Not little, a lot of pain. Excuse me. Now, let's just close the final two components. And the first one that I would like to spend a few minutes to explain to you is a cylinder. And like I explained in the very much beginning of today's lecture, this is what you can find in one extreme of your hydraulic circuit. So it's converting the pressure to be forces that are applied to a mechanical system. Equations that are needed in a hydraulic cylinder modeling are very simple. You just need to know the dimension of the cylinder, the cross-section area of the cylinder. Well, it comes from the dimensions. So the cross-section area of the cylinder and the pressure that is applying in a cylinder piston side. So that's going to be the P1, which is here, and that you can get from that first order differential equation we discussed earlier. Then in a piston rod side is a similar procedure. This time you need to know the cross section. That is a piston minus the cross, there's a piston rod, and that's denoted as a cross section area 2, and the pressure that is applying in that particular section. Those are the 4 parameters or 4 components you need. 2 of them will come from the differential equation, and rest 2 are coming from the dimensions. Now the final 5th component, that's something that is a little bit of painful thing. That's the friction. Friction typically is somewhat small in hydraulics, so it's not playing that significant role, but still in order to make accurate physics-based model, it is a good idea to account that too. How you can actually count that? Well, I will explain that, or a simple procedure to account that in the next slide. But where this friction is actually coming from? Well, the friction is coming from due to the sealings. There's a sealing that prevents oil to get off from the cylinder here. And then there's another type of the sealings that make sure that the flow is not traveling across the piston. So those are the 2 sealings that are used in real construction. And because of the sealings, there is a friction that is the components on this part of the equation. Now this particular friction is behaving according to stick-slip behavior, or there is a stick-slip phenomena. Have you heard that before? Stick-slip phenomena. You haven't. Okay, so it behaves such the way that if I look at the equation, let's look at the equation in a second, but let's first take a look at this picture here, and let me make this a bit bigger. You know what, I need to apologize that this is written in Finnish, but maybe we can make this as a part of the the Finnish lecture. What I have here in x-axis is velocity. This one, it's velocity. It's in Finnish. It's nopeus, but don't mind about that. And then what I have here in y-axis is a friction. So that's Kitka. But let's focus on the subject matter. Let's leave the Finnish language another class. Okay. Now, when you look at how this friction behaves, first of all, the first observation, which is critical, is that it is a function of velocity. So it's not staying constant as a function of velocity. But it behaves a little bit of unusual way, because typically the friction is modeled in such a way that there is a velocity multiplied by friction coefficient. Let's call that as a, maybe d. And then, that means that there is a linear relation between the friction and velocity, meaning that is something like this. And the d that was used in my equation, that is defining the slope itself. That's what you use to deal with. Now, in this case, it's obviously a little different because, it started here, having certain value when the cylinder is standing or when the piston is standing. And as soon as you start moving, what happens is that the friction goes down and you are moving downwards. Slope here is a negative. And then you reach a certain point and they started to increase again. This is a behavior that is called stick-slip behavior. And it causes a motion that is motion that makes kind of funny noise, like typically kind of like a noise that you can hear that there is a sliding and then things stop and then it's sliding again and stopping, sliding again and stopping. Let me see if I can make your demonstration. No good. Let's try this. Not the good one, but still you hear that noise. Okay, so let me see if, here. This is the best. Okay. Not great. So let me see. No, not so great. Okay, so what happens is that, what I try to do is that there is like when I'm looking this, kind of these legs of that seat, when I was pressing, there was a lot of force from my hand, big F. Then I was sliding, this direction. What was happened like in a microscopic level that there was a sticking here, and then when I was pushing more force to this direction, they was bending a little bit, and then it was just sliding, going to this part of this friction curve, and then as soon as it was sliding, it was stopped again. And that's what makes that funny noise. That's kind of like a braking noise. And that's because of that stick-slip behavior. And that's simply because, the friction, standing friction or the static friction is higher than the sliding friction. So it's moving between the static and the sliding friction, and because the static friction is higher than the sliding friction, that's when it's moving, stopping, moving, stopping. It is called stick-slip phenomenon. Clear? Would you like me to push this seat more back and forth so it's clear? Please don't. Okay, so I don't. Okay, I don't do that. Okay, so let's go back here. Now, how in a modeling wise, how is that we can make it happen then? Well, the easiest way to model the friction is this. You have here pressure and corresponding cross-section area. This is a net force that the cylinder is capable to produce. That is then multiplied by the another part of the equation where there's a 1 minus efficiency of the cylinder. Efficiency typically having the value like 0.95, even higher than that. So that gives you here, the value that is 0.05. So the force produced by a cylinder is multiplied by a value 0.05, 5% roughly. And then is multiplied by the curve, which is having just the values maximum 1, and then 0. And that is replicating this motion. So it's like, let me make it clear again. So let me go back here, and let me take everything off. So this function here No. Okay. Oh, so it's still at this erasing phase. No. Not that. No, it seemed for some reason. Yeah, this function, this one here is just a value that follows this curve. So it started from the 0, goes up here, and it behaves like that. And then, this maximum, these values are wanted maximum, and that's it. There's a detailed explanation in the lecture notes. Okay? But you're happy with this. So this is kind of like symbol representation of that stick-slip phenomenon. All right? You good? Now you are a bit confused. They are not in class quiz. You're doing this. Others? You're not doing that.
Your question was now you are a bit confused and I said yes.
Oh, okay, so you're confused. Okay, so let me just shortly summarize this. So overall objective here is to be able to model the friction according to these measurements. How we gonna make it happen? We're gonna first of all, compute how much force cylinder is capable to produce. That force is then multiplied by efficiency, or inverse of the efficiency. Say that if the efficiency is 95%, then the net force is multiplied by 5%. So from all the force is 5% is maximally going to as a friction, okay, because it's related to efficiency. And then in order to replicate this motion here, all that is multiplied by curve that is polynomial curve in such the way that here, this is just a scalar number, which is a 1, and this is the one that is associated to velocity. So those are the three components. Clear? Not yet.
Velocity and the
Then,
force and
then this is just a value that in maximum case can have number 1. So it's a function of velocity. If this would be just a conventional friction, then this value would be like this. But now I'm making the polynomial expansion in such the way that is following roughly that curve. Roughly. Okay? Good?
so that number 1, the 1 is frictional force.
It's kind of frictional force, or it's just what this polynomial expansion can have as a maximum value. So in the worst possible scenario, the friction will be net force produced by cylinder multiplied by 0.05, and then this will give you 1.
Okay.
So
that is this zeta.
yes, correct. That's what it is. Correct. This one. That's what it is. Okay. So then the final component is a pump. Now this will be somewhat brief as well, and then we're gonna ready to move on to flexible bodies. So I will spend, let me think, 15 minutes to explain you pump. And then there is a question that is asking, listen to me, in the next in-class quiz I'm asking, mathematical modeling perspective, what is that the pump is producing? And the options are, several options like voltage and so on and so forth. But what it's doing for us is that it's producing flow rate, like I will explain. Okay, you can write already flow rate. Flow rate, that's the correct answer. Okay, but because this is serious, it's serious business now, because this is last opportunity. So it's either going to happen or it's not going to happen. I see. We'll see how it goes. But, the pump. Now, the pump, in a modeling perspective, it is considered as a flow source. It's something that is producing the flow to system. And now this is a bit confusing, like producing the flow. So where is that the pressure then is coming? Well, it is coming when you're restricting the flow rate. Because remember, in this equation that we are already familiar with, I have here effective bulk modulus, the volume size, flow rate in, and the flow rate out. And now, if you have a pump here, let's make this kind of drawing here, and is keep on producing the flow rate. It means that there is incoming flow, and there is nothing that leaves here. If you just have here dead end, like this, the pressure keep on increasing because this differential equation will have positive value, and once you solve it, the pressure keep on increasing as a function of time. So that's how it behaves. So it's not directly pressure source, but the flow rate source. It is producing flow rate. And that's exactly what we're gonna take a look. So we will look how is that we can describe this flow rate in different kind of pumps. And generally speaking, we have two different options ahead of us. So we can have fixed volume pump or variable volume pump. In a fixed volume pump, the pump keep on producing the flow rate to system no matter if it is needed or not. So it's keep on doing that regardless of the need. Then there is a variable volume pump that is looking whether or not there's a need to have more energy in the system. And then there is even more clever versions of variable volume pumps that are load compensating pumps. We're going to look those as well. But fixed volume pumps or variable volume pumps, those are the two basic choices. And they will have very different approaches in modeling perspective. Okay, so this is how the pumps look. When you look at the structure itself, we are not going to take a look at that too much. Typically, we are looking at the piston pump. So the idea is that the piston is going back and forth, and the piston, when it's moving that direction, it is sucking the oil to system, and when it's coming back, it's pressurizing the flow, and that's how it behaves. So that's a typical scenario how the flow is produced in hydraulics. Okay, now if you're dealing with that simple approach or simple pump type, which is a fixed volume pump, then pretty much only you need is this equation, which tells you that the power is equal than the flow rate multiplied by pressure. That's pretty much all equation, or this is what you need, because the setup in this kind of pump is such the way is that there is a motor that is running the pump, and the motor is keep on producing this power to system, and due to that, the flow rate goes to system regardless of if it is needed or not. So that's basically how it goes. Now there is a limit, because there is always physical dimension of the pump, and the pump cannot produce more than what the physical dimensions are limiting it. So that's why using this equation with help of efficiency factor, and then using the fact that there is a physical limit how much flow the system can produce, you can have a fixed volume pump model that consists of two equations. The one, again, that is based on this power production, and you have here efficiency, and the set pressure, and the set pressure is where that you would like things to be, how much pressure the system is assumed to be produced. And then there is this maximum flow rate that is coming from the dimension. So you compute these two values from these two equations, and then you select the one that is producing the lower numerical value. Simple like that. So it's not very complicated model. What about a bit more advanced model? This variable volume pumps. Well, those are the kind of the constructions that the flow rate is no longer constant, but it depends on the settings. And now in order to understand that, we have to look at a little bit about, how things are made. And that I will explain you right after the break. And right after the break, we're gonna look a little bit about YouTube videos, which explains you about load sensing pumps. This is something that is critical to know as well, because particularly in mobile applications, the load sensing pumps are very frequently used. Okay, so now we're gonna have a break of 15 minutes. Then I'm gonna close the case of pumps. Then in class quiz about what is that the pump is producing. So what it is? Flow rate. And then if it is not correct, if it is not 100%, then it's not going to be 100% in this year class. And then we're going to move on to flexible bodies. Okay, so let's have a break. So is it all right if we do this in like a proper way, that there is a break of 15 minutes? What is it you're saying? You're saying that, okay, 15 minutes. Okay?